Welcome everybody to CSI 45, week 3, day 2. And this is a famous Unix program called CMatrix, where it turns your terminal into a matrix-like display. My newest Raspberry Pi has arrived. It is called a Pi 400. It is a goofy looking machine. The normal Pis are small and compact, fit in the palm of your hand. This thing, just give me a paper cut. This is the machine. So there's actually a Raspberry Pi built into the under case here of the keyboard, and so this is actually a Raspberry Pi that's actually faster than the current server. And so my plan was to just have this hanging off my bookshelf like the other one, because the other one has a fan running all the time. This one is actually passively cooled. One of the nice things about this large backplate here is that by gluing the system on a chip and stuff to it, it dissipates enough heat. It doesn't need a fan. So if you want to look at the side of it here, the Pi 400 is also a lot cheaper than a Pi 4, which is a bit weird, because it comes with a lot more, you know, and it comes with a power supply and a mouse of all things. But it is just kind of goofy looking. Like, I kind of wish they just made it like a passively cooled because it's a higher clock rate. Also, it actually is a faster processor than the one I have on the server right now. I wish they just made a large passively cooled one that doesn't look like I'm gonna have a keyboard hanging off the side of my closet. Maybe I can like duct tape it to the back of the bookshelf or something. I don't know, so nobody can see it. But here's the side of it here. Here you can see sorry, it's a mirrored video. Here you can see all the GPIO pins. This is what we're going to be talking about next week. We're going to be doing physical computing, and these things can have sensors hooked up to them and can control motors and things like that. And this is part of what makes a Raspberry Pi like a project, a hobbyist's computer, rather than it just being a very small, very cheap computer. Do you have a cat? No, I do have a kid, but she's beyond the point where she would just. No, actually, I take it back. I showed this to her and she immediately picked it up and started hitting keys on it, which would be perhaps dangerous for you. You're doing your homework, Simon. Suddenly the server reboots itself. I don't know. But here you can see it's got two HDMI. They're mirrored. Two HDMI outs, so you can actually have two monitors set up with it. It's got an SD card here. That is power, which is USB-C. It runs all of its power just through a USB cable, kind of like a cell phone. And then you got two USB-A ports here that are high speed and one regular speed, or perhaps vice versa. I think these are USB 3s though. And then it's got Ethernet, and it's got a security lock, so you can actually lock it down. So if you want to buy these for a computer classroom or something like that, you can just have a security lock. Then all you have to really do is have the power supply plugged in, HDMI, the mouse comes with it, and you've got yourself actually a decent enough working computer for not a whole lot of money. Like, the Pi 400s are supposed to be, I think supposed to be more expensive, but like, let's check out Amazon. Amazing. Nope. Why do you do that to me, Amazon? And so they're around 100 to 150 right now. See all buying options. 150. Yeah. So this is supposed to be a $35 computer, and so they're currently being marked up. Was that like 4 times, quadruple their list price? And even still, they're out of stock. Like, if you go to the official Raspberry Pi website, like, you can't get them. They're supposedly getting more in stock in March. Raspberry Pi laptop, $500. Yeah. So this electronic shortage we got going on here is a thing. And look at this, like the Raspberry Pi 400, which is more, it's just more in a lot of different ways. It's got faster CPU, it's got a power supply, it's got a mouse. It's $99. So if you're willing to put up with the goofy look, it's actually, I think it's just because people don't know about it. Is my only guess. So, yeah. If you guys want to get one of these for your own amusement, you can do so. Let's see. Does it come with even a memory card? Yep. So it comes with a 16 gig memory card with the Raspbian operating system already installed on it, and it's got a memory card reader, so you can plug that in to your PC. If you have a full-size SD card reader on your PC, you can plug it in and flash it, things like that. Okay, so yeah, well, I'm debating whether or not I want to switch the server over to that, because it is going to kind of look goofy, but at the same time it'll be quieter, so who knows. All right, let's continue our discussion of yeah, and that's the only color. Yeah, it's not like you get, like my current, your server right now is that box hanging off the side of the bookshelf right there, and it's in kind of a cable won't quite reach. It's in a little stylish black box, and I don't necessarily want to have a white and pink keyboard hanging off my bookshelf. I want to build a pie hole, so you just might. Yeah, pie holes are pretty cool. Do they not make pie 4s? They do. They do. They're just out of stock. Like the electronic shortage we've been having for the last year or so has been just having these wild ramification consequences just all over the world. Just somehow, like, all of our production capabilities for computers were just not enough. So, partly maybe cryptocurrency miners are part of it, and now with Bitcoin collapsing, apparently it's pretty easy to get a graphics card these days. So, I don't know. I don't know if you want to buy an old cryptocurrency mining 3070 or something, but okay. Yeah. Bitcoin, at least it was the last time I checked. Opened at 38, closed at 36, so it lost almost 10% of its value in the last day. Bitcoin was at 50,000 a month ago. It's at 38,000 now. So was it 66,000 2 months ago? 36,000 now. So a lot of people are starting to like dump their Bitcoining rigs and things like that. Yeah. All right, buy the dip. Pi Zero is still a reasonable price. Yeah, Pi Zeros are I mean, they are pretty underpowered, all things considered. All right, so let's do this. Let's do more assembly homework, or assembly learning. All right, so last time we talked about arrays, and basically, when you do work with arrays, if you want to have like a statically allocated variable, you make what's called a data segment at the bottom, and then you can put variables down there. And these don't have to be like arrays. You can just put regular variables down there too. And then you can use the load and the store commands to read and write to those variables as well. So if you find yourself running out of registers, you can use LDR and SDR to read and write to them. So it's a two-step process though, and RAM is slow. And our computer architecture talk is going to be on just how slow RAM is. But you can see, just as a first approximation, if you want to print a string, you have to first load the address of the string. That's what that equals print string means. It means you're loading the address of label print string. Print string's down here. It's going to load whatever memory address the A is at. The first letter in the string is the memory address of that string. So where the capital A is the memory address. I don't know where it is. You don't know where it is. It doesn't matter. That's why we do this. It just makes it easy to write the code. And so that will put a pointer. So R0 is a pointer, essentially at this point. It's a memory address. It holds the memory address of a character. And then this is loading into R1 base plus offset. So whenever you do memory operations, you have a base, which is the start of the array, and then an offset, which is how far into the array you want to go. And in assembly, how far into the array you want to go is bytes. In C++, it's in elements. So if you go 5 ints to the right, that's 20 bytes to the right. And I always get those confused because I'm used to doing square bracket 4. And so I'd put like a 4 there instead of the R6, you know. And I'm like, why is my code not working? Okay. So, yeah, it's a 2-step process to load like R. Where's R? Okay. So this is the base, the beginning of the array for R. Put that into R1. And and then the offset is R6, which is how many bytes to the right we are. And then this is the syntax we use for reading and writing to an array. So base plus offset. There's actually plenty of other options as well. You can do, like, if you want to optimize it, a very common optimization is to do base plus offset with write back. So if you put like an exclamation mark, then it will move the pointer, as well as reading from it or writing to it. It also moves the pointer at the same time, and that way you don't have to constantly do like a multiply or whatever. You can just have the offset be 4. And then if you do it with write back, the pointer moves, and as long as you're okay with the pointer moving, then it's substantially faster because you do repeated addition instead of every time having the base and then you have to recompute the offset, which is a multiply, which is 4 times slower. Right? Let's see if I can find this in here. Write back. Yeah. Load story. Page 62. That's not the right section. Well, the more advanced options can be found in your textbook, and there's like a bunch of different ways you can like read and write to RAM. I'm only going to teach the basic way, which is you pass in a pointer, you pass in comma. This is the pointer, and then you pass in how many bytes to the right of that pointer you want to read or write from. You wrap it in square brackets like this. And then it will store the value in R5 into that memory address in RAM. And if you do an LDR, it loads from that memory address in RAM. And str is the only command where the source register is on the left side, and the data goes this way. Okay. Any questions about this? So this loads from this pointer, that offset, and it puts whatever's in RAM there into R1. If you want to load 32 bits, you use LDR like this. If you want to load 1 byte, you do LDRB, LDR byte, and it gives you a single byte into R1 or whatever. No questions? It's all pretty straightforward. Okay. Let's look at dynamic arrays. See if you guys are ready for that. Yeah, I think you should be fine. Okay, so second parameter is not the size of the array. When you do a load or a store, R1 is a char star pointer to the start of the no, R0 is. To the start of the string. And then R1 is equal to R square bracket 10. And it computes this, so R1 is R before we change it, and R6 is the offset. So let me maybe sketch it out for you. This is a very common way of doing memory stuff in computing. The USB cable got stepped on, and now the tablet kind of cuts in and out. And maybe get a new one. Okay, so let's say you got an array. Like, let's just do C++ and just say you got like int star array equals new int 10. We'll just make 10 integers. What does new return? What does the new command return? In C, it's called malloc, by the way. This would be identical in C, except this would be called malloc, and you'd pass in 40 to malloc. Malloc just says, give me 40 bytes. C++, you just say, you can actually make it typed. Same code, essentially. It's a memory allocate. Yeah, memory allocate. Yeah. So what does new return? What is the type of new? Like what is the type of new int square bracket? What does it return? What does new do? What does malloc do? It's the same thing. So in a computer science program, well, it's a bit redundant, but your typical view is you got your stack up here, you got your code segment down here, you got your like data segment for like your statically allocated stuff here, and then above that you have the heap. Okay, and the heap grows upwards, and the stack grows downwards. That's our traditional view of how memory works on a program. Okay, so segfault. No, it's not going to segfault probably. What happens when you do this is that it says give me 40 bytes off the heap. So these are called heap allocations. And they do the same thing. Malloc returns a void pointer, technically, but we ignore that. So for now, both these things do the same thing. And what it does is it says find for me somewhere within the heap, find for me 40 bytes. And this is a program that keeps track of which chunks of RAM have been allocated, which chunks have been deallocated, and it finds a suitable chunk of 40 bytes and says, aha, I found a spot right here that's just perfect for you, and then it returns that memory address. And so what it's going to do, it's going to return the beginning of 40 ints. So this is going to be 40 bytes long, or sorry, 10 ints, 40 bytes. I drew too many lines here. Show that whole. a little better looking. So what it does is it finds somewhere within RAM, within the heap segment, a spot where 40 bytes, or i.e. 10 integers, is available, and the address of the first one, the person we know as r square bracket 0, the memory address of that is returned. And so it's going to say you are at memory address 1000. Okay? And so it's going to just return like the number 1000 or whatever. And obviously this just depends on wherever it finds an open spot. And if there's no open spot, then it calls Sbreak, which you guys don't know about yet. And what it does, it actually moves the segment boundary upwards. So it actually increases the size of the heap. And if you ever run out of heap space, then it kills your program. Likewise, the stack moves downwards every time you do a regular function call with a normal variable that gets allocated on the stack. So if you have just regular variables like int x, y, z, all of these come off the stack. And the memory is allocated automatically off the stack. And when the function returns, they're automatically erased off the stack. With new, this memory is permanent. It's permanently allocated until your program goes away or you free it. Okay? It is guaranteed to be a consecutive memory address, yeah. And so to free the memory is like this. You say delete square bracket r in C++, or you say free r in C. So this is C, C++, they do the same thing. Okay. C++ is preferable because it's typed, right? Like this returns a pointer of type int pointer. This returns a void pointer. There's no type on this. You have to make sure you don't, like if you have like a float pointer here, everything would get screwed up. The whole reason why we have a type system is so that we can catch errors, right? Like that's why types exist. Like you might see from your time doing assembly already that not having types actually is rough. Sometimes it gets in your way. Like sometimes you want to do really horrible things and treat a float as if it was an integer or something, but those are far and few between. C world is weird. It's got its own way of doing things. Put it that way. Okay. So when you call new or malloc, it doesn't matter. Let's say it returns 1000. It's up to you to remember, by the way, that you have 40 bytes. You got to write that down somewhere. Write that down, right? It returns to you the start of 40 bytes, but the fact that you have 40 bytes, you have to keep track of yourself. It is a pain to do, because if you screw that up, everything's going to go bad, like real fast. Okay, so then when you want to access this, you can say things like r square bracket 3 is equal to 420. Okay, so this is r0. So array square bracket 0 is at 1000. So this is 0, 1, 2, 3. So 420 is going to get written into that RAM address. So what is the RAM address here? What is the address of 0, 1, 2, 3? What memory address is that? Question mark, question mark, question mark. If array square bracket 0 is at 1000, what is the memory address of array square bracket 3? This involves highly advanced mathematics. But you guys are in college, so you should be able to do it. So the next one, no, it's not. Array 1 is at 1004. The next one's at 1008. This one is at 1012. So this is what we call the base. Like anytime you see somebody online saying based, this is what they're talking about. And the offset is how far to the right of the base it is. Okay. And so the offset here is 12. Okay. It is 3 integers to the right, i.e. 12 bytes. So the base is 1000, the offset is 12, therefore the memory address is base plus offset, which is 1012. Okay? Make sense? In assembly, it's going to be something like this. You're going to be doing like a load into some register, R0 doesn't matter, and then the base, let's say the base is held in R8 and the offset is held in R9, then it'd be LDR R0, square bracket R8, R9, like that. And then it adds R8 and R9 together. It actually doesn't matter which one you do first, by the way. You can do R9, R8, but it's traditional to put the base first and the offset second. And then it's going to go to that spot in RAM, load the value of 420, and R0 will be set to 420 after that. Okay? It always goes up by 4. How big is an integer? That's your question. Yeah. Ints aren't always 4 bytes either, but on our systems they are. So, yeah, let's talk about other types. So if you have a double array, size 100. First question, how big? How much RAM does this array take up? Can you use R7 to hold a value? Yes, you can. That's why that was a wrong answer on the quiz. R7 is just a regular, it's just a regular register. Yeah, a lot of people think you can't use R7 because it's used for the system calls. No, it's a regular register. When you do a system call, it checks the value in R7. That's what makes it special. But if you're not doing system calls, it literally doesn't matter. So 800? Yeah, okay. So a double is 8 bytes. So 100 times 8 is 800 bytes. Okay. Let's say the base is at 4,000. So let's say R holds the memory address 4,000. What is the address of R square bracket 0? If R holds the memory address of 4,000, what is the memory address of the first element in the array? Thank you to students that responded. It is in fact 4,000. That's what the address of R and the address of R square bracket 0 are the same thing. So R is equivalent to the address of the first element. Okay. That's how arrays work. There's not a separate thing. The base is at 1,000. The address of R square bracket 0 is 1,000. Same memory address. Okay, so what is the address? What is the address of array square bracket 2? And Singh and Vargas don't respond. Four is incorrect, but thank you for trying. Remember, the address of R is 4,000. So what is the address of R square bracket 2? Remember, the address of R square bracket 0 is 4,000. So the address of R square bracket 1 is 8 bytes to the right. 4,008. The address of R square bracket 2 is, let's do the math, base plus offset. So the base is the base is 4,000, and the offset, every double is 8 bytes, and we're doing element 2, so 4016. The offset is 2 doubles to the right. A double is always 8 bytes, so 16 bytes to the right. Yeah, this is a double array. All right, let's do this again with long array of size 10. And we will say R is equal to 5,000 this time. Let's make it harder. It's equal to 1, 2, 3, 4. Okay. What is the address? What is the address of array square bracket 0? What is the base address? One, two, three, four. Good. Okay. So what is the address of array square bracket 20? Why is it 1, 2, 3, 4? Because that is what R is equal to. The address of the first element in an array is the same thing as the memory address held in the pointer. These are always the same value. When you have a pointer, the pointer is pointing at the first element in an array. That's literally what a pointer is. A pointer is pointing at the first element in the array. Okay. So the address of array square bracket 0 is equivalent to the base, which is what we call R. Okay. So how big is a long? $16 bytes. Awfully impressive. No, there are no 16-byte types. Good guess, though. Please participate. 12 bytes? Nope. There are no 12-byte types either. In C++, the longest types you're ever going to see are 8 bytes, because we have 64-bit systems, and there are no 128-bit systems yet. Maybe never. Who knows? And someday, I guess. But, 8 bytes? Wrong. 4 bytes? Wrong. 32 bits or 32 bytes? Or a byte is 8 bits. And it is not 32 bytes for sure. Okay. Is it dynamic? No, it's not dynamic. It is different on systems. Very good, Mr. Singh. So, yeah, the size of a long depends on which system you're on. Do you guys know how to find how big something is? So there is a built-in function. This is actually part of the language. It's actually not a function. It's actually part of the language in both C and C++ called sizeof. And it tells you how big a type is. So if you compile it and run it, 4 bytes. Bencourt. We do this again on the other server that I have. It's 8 bytes. Same program, different result. This should scare you a bit. Because the whole point of C++ is that you can, have it on different systems and it runs the same way, right? If we wanted to just write something for one computer, we would use assembly, you know what I mean? Well, there's other benefits obviously as well. But the whole point of C++ is that it's portable between systems. And the basic types are not very portable. Some of them are. A char is always 1 byte. It's defined to always be 1 byte. But like a long on our Raspberry Pi, it's 4 bytes. On the main server for the other classes, it's 8 bytes. And so that means you take the same program and you move it between systems, and it behaves differently. The the maximum integer you can hold obviously is different between the two systems. And so, yeah, and so that's why I don't recommend using longs. Like I'll still use int because int's like vanilla ice cream, but ints can be actually 2 bytes. Ints can be shorts. And so that would give you a total of negative 32,000 to positive 32,000. And that is a wild thing to discover when you port to a system that has 16-bit ints. Because you're used to having like plus or minus 2.1 billion to play with. Not anymore. Not anymore. You're using an integer to track your money in a video game. It's going to overflow at $32,000. It's quite different from overflowing at $2.1 billion, you know? And so I recommend actually not using, I mean, you know, if you're doing like, you know, something done like this, right? I equals 0, I is less than 10, I plus plus. Like, if you're doing something like that, like knock yourself out, you know what I mean? Like it's fine. But like if you're actually using it to like hold values, and these values, you want it, you have kind of in your mind a range that they should be in, don't use enter long, because they can switch between platforms. And so what I use instead is, for example, unsigned integer 64, and I do this instead of unsigned long. Or I think it's shorter. You can see they're both 8 bytes, 64 bits. But this one, like, I like using this system because you just tell C++ how many bits you want. I want a 32-bit integer. Thank you very much. You know what I mean? Like, give me a 32-bit integer. And it is more typing than long. But whereas long could sometimes be 8 bytes and sometimes be 4, this one will always be 4. And so you don't get any nasty surprises when you move between systems. So there is no long. Yeah, unfortunately. I was kind of hoping that there would be like a double, you know. But unfortunately, there is no double. Double animal style. Slice of auto. It's not going to compile either. Invalid use of auto, Mr. Knight. Yeah, because auto isn't actually a thing. Like, it looks like a thing, but what auto means is like my type is the type of somebody else. It's just copy their type into me. And so if we have like auto x is equal to 10, and we say what is the size of x, then it's 4 bytes. All right, and so sizeof takes variables as well as types. It's a built-in, it's an intrinsic function that returns the size of something. Which one of us is going to bring up long? Somebody say double. I did. There is no double type in C++, Nico, I'm afraid. So, yeah. And so if you want to shorten this down, you can always do using I32 equals int 32 type, like that. And then you can make variables of type I32. And this is very common. All right. So it's very common to have aliases set up for every size, right? So you can have U64, you know. You do Unreal Engine programming, they got all these things set up to do this via uint 64T. It's defined but not used. Yeah, I know. So there you go. 64. No quad type. At some point, I suspect we're going to move to 128-bit computers. Although, remember, every time you add a bit, you double the range that it can have, and so the difference between 2 to the 32nd power and 2 to the 64th power is massive. Like, it's actually a really giant jump up in the amount of RAM you can have, because every bit you add doubles it, right? And so, at some point, we've technically had 256-bit computers before. There was something called Itanium, which is sort of a failed approach by Intel and Hewlett-Packard to make 256-bit CPUs 20 years ago. And they were used, like, in servers a little bit. They finally got discontinued just a few years ago. They've actually been in production, but they just never caught on because they were not backwards compatible. Terabyte of RAM for what? For I mean, think about it. Like, if 32 bits gives you access to 4 gigs of RAM, right? So 33 bits gives you access to 8 gigs of RAM, right? So when you go from 32 bits to 42 bits, that takes you up to like 4 terabytes of RAM, and you just keep scaling that out. Like, so you're talking like, what is it, like 10, probably like 10 significant digits more of RAM. So 4 gigs times 10 million, I don't know. It's a large number, right? Of how much RAM you can have on a 64-bit system. In theory, like, nobody can afford it. Right. Okay. So to come back to our point here with base and offset, what is the address of R square bracket 20? Chrome will still use all of it. Yeah. My RAM. Yeah. 1294. No, not 1294. Yeah. So we have 1 vote for 1294, which is wrong. We have 1 vote for 1314, which is 80 bytes. So he's going for 2 votes for 1314. I didn't see what system this is running on. 1312. What system is this running on? I didn't say. So, 32-bit system. The Raspberry Pi. See, that's the thing, right? This is actually not a well-defined question because longs, are 4 bytes on one system and 8 bytes on the other. Yeah, if it's the Raspberry Pi, then 20 longs to the right would be 80 bytes to the right. So the offset, the address of array 20 is the base plus 80 to the right. Okay. So it is 12. It is 1314 if we're on a Raspberry Pi, and it's 1394 as Mr. Shahab said if we were on a 64-bit system. Okay. You guys understand this? Base plus offset. You guys cool with that? Maybe I'll assign our first textbook reading for like Tuesday. That might be a good break between programming assignments. So I think I'll give you guys the weekend off. Just read the textbook. I'll put up a quiz. Okay. Because I want to kind of get you guys into C world a little bit more. Okay. So when you do a malloc, it finds 40 bytes of available RAM. If there isn't any, it does a Sbreak and moves the thing up and allocates the 80 bytes off that. New is the same thing. And then when you say free, what happens when you do a free is that it opens up that 80 bytes back up for usage by other people. So the malloc and free, basically behind the scenes, they have a giant data structure, and the data structure is keeping track of open chunks of RAM. And so when you allocate RAM, it's like it marks it off. It's like, okay, that range there is used. And then when you free it, it marks it as being open. And if there is an open area next to another open area, they combine into one larger open area. It's actually a hell of a algorithm to write. Junior level computer science at UC Irvine, they studied just how Malloc worked for like a unit, and then they had to write their own. It's not a small function. Yeah. If we do dynamic arrays in assembly, is it faster than a vector? I mean, what do you mean by faster? Like to allocate? I don't know. I mean, if you do a static array, it's faster, because a static array, like when you do dot skip, that's allocating memory off the data segment, and so it's always allocated. It doesn't take any allocation time at all. But if you're talking about like a vector, like you do a new and you do a free, and a new, a copy, and a free, it's probably, are you using Malloc, then it's probably going to be about the same speed. If you're not using Malloc, then it'll be faster, but you're going to lose the benefits of Malloc and free, which is the fact that it keeps track of what chunks of RAM are open. So if every time you do a new, you do an Sbreak and you just move the heap pointer up, eventually your code's going to run out of RAM, right? Because it only goes up, it never goes down, and you never reuse stuff that's been freed. In some industries, though, Bencourt, that's actually how it works. If you are working in aviation, you are not allowed to allocate memory when the plane's off the ground. So no pushbacks, no news, no Mallocs. When the plane's off the ground, nope. All that memory had better be allocated already. So the reason for that is because you don't want the plane to be running. It's like, okay, let's allocate some new RAM to store our airspeed data, and then it's like, oh, no RAM left, and then the plane's like, well, I guess I'm gonna die now. So yeah, for planes, if they're going to new stuff, all that takes place on the ground, and they're well defined how much RAM they need. Like this program uses 123.2 megabytes of RAM, and they know exactly how much RAM, and when they turn it on, it does its allocation, static or heap allocation, doesn't matter, but it does it at the beginning, and then it reuses those arrays the entire flight. So it might only be able to hold 123 data points, and then when it runs to the end, it goes back to the beginning and overwrites the old ones, and so you have a history of the last 123 data points and no more ever. So yeah, so it depends on your industry, where like sometimes you just don't ever Malloc or free at all. Like you allocate them all at the beginning, and just and you define and in your program, I have an array of size 100 and no more and no less. 100, make sure that doesn't, that's enough, and that if we go over, we handle it, like we wrap around to the beginning again, or something. Okay, so how do we do this in ASM? So in dynamic array, so the code we're going to do is we are going to read in a integer from the keyboard. We're then going to allocate an array of that size. So if they type in 100, we allocate an array of size 400, right? Because we're making 100 integers. I don't know if that's correct, but it doesn't matter. And then we set square bracket 100 to be equal to 53 and quit. All right. So we call, this is again linking against the C functions that do our IO for us. So we read an integer from the keyboard, and when you call a function, the return value is put into R0. So we're going to move out of R0 into R4, and then we multiply it by 4. If you have a number, you shift it left once, it's multiplied by 2. You shift it left twice, it's multiplied by 4. Every left shift is a multiply by 2. So Sbreak is, I was just showing you that a second ago. So Sbreak increases the breakpoint of a program. and Point Break, Keanu Reeves, great movie. And so it's basically the top. It's the top of the heap, if you want to think of it that way. So every time you call Sbreak, you know, Sbreak 100, Sbreak 200, moves up by 100, moves up by 200. Okay. And this is the thing that Malloc uses. So normally in C world you don't use Sbreak, you use Malloc. And Malloc will make a call to Sbreak when it needs to, but it keeps track of all the free areas and things like that. Okay. And you can read notes on this. See also break. Yeah. So Malloc basically calls Sbreak right when it needs to, and for our purposes, and it returns the start of the chunk of memory that was allocated. So we say, all right, give us 400 bytes. And so we put 400 into our 0. We call Sbreak. Sbreak moves the pointer up, heap pointer up 400 bytes. We then check to see if it returns -1. -1 is returned if it failed. If you ran out of heap space, it'll fail. It's not technically a heap because there's no data structure. Like, it's just a segment. It's just a chunk of memory and it's just going up. So if we run out of room, die. Otherwise, we write this is going to be a pointer. So when you say, hey, give me 400 bytes, it returns a pointer to the beginning of the 400 bytes. And we're just going to save that as our base. And you're back, headed right home from CCC. Hour and 15 minutes after class starts. Okay. All right, so then we're going to write the value of 53 into memory address base plus 400, or element 100 of an integer, right? Okay. And so this will very happily go out of bounds. There's no bounds checking in assembly. You got to do that yourself. But do you guys understand the syntax for store? So this is the value we're going to write. We're going to write 53. It's on the left-hand side for a store. It's backwards. It's the only command where it's backwards. And we're going to write the value 53 into that RAM address there. Okay. You guys understand? So this way you don't have to use the .skip thing if you don't want to. You just dynamically allocate RAM for yourself. Stir is assigning an array a value. It's doing this command right here. So 53 is held in R1. A pointer, the array pointer is held in R5. And the offset of 400 bytes is held in R2. 100 integers, which is 400 bytes, is held in R2. Okay. So, I'd like for you all now, in lab time, to write stir command. Yeah, this is why I always tend to stick to this format, because like I said, there's actually a lot of different ways that you can do it. Like you could, like this would work. For example, that would, I don't know if that would work actually. But yeah, if you put an exclamation mark after it, then it moves the pointer, which saves you on having to constantly do multiplies and things like that, as long as you're willing to destroy the pointer, or you make a copy of the pointer and then use write back like that. If you put it after the, if you put it outside of the square bracket, that's a different thing. So just look through the textbook for all the different versions. This is the basic one, and that's the one that I stick to. So I'd like for you for lab time to dynamically allocate a array and fill it with powers of 2. So fill it with 0, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, etc., right? This is in 17, yeah. So I'd like for you to allocate room for 32 integers, and then set each one of those integers equal to a power of 2. Let's start with 1, actually, not 0. So 1, 2, 4, 8, 16, 32. Okay? And how much time do you guys want to have for that? This class goes until 12:30, I think, right? $12.50. Okay. So just got here. Jeez. What do you guys think? 40 minutes. Should that be enough for you to do it? 17 is the one you should start with. So that's a good starting point there for you all. So I'll give you guys till noon. Okay. And so what I want you to do for lab time is start with 17 dynamic arrays.s and do the following. Use Sbreak to allocate 32 ints. Fill the dynamic array with powers of 2. So 1, 2, 4, 8, 16, 32, etc. And print. You have till noon. And then we will talk about classes. Do object-oriented assembly. Sbreak is the same as using new or Malloc. Yeah, except if all you're ever doing is newing, yeah, it's going to be identical. Malloc though, like, so it gets tricky when you do a free, right? Because like, let's draw out RAM here, right? So here's a big chunk of RAM, right? And it's all available at the beginning, and your breakpoint's down here. And somebody says, "Hey, give me 100 ints." And you're like, "All right, cool." So this goes up to here, and you've now got 100 ints, right? Everything's cool. And you're like, "Hey, give me another 100 ints." So this moves up, and you got another 100 ints. And then they free this one. You can't move the pointer down, right? Because the data pointer, the segment pointer is still here. Like it's like this is still valid RAM, but this has been unallocated. And so if somebody now asks for another 100 ints, you don't want to move this up because that would be wasteful, right? Instead, what you want to do is recover and reclaim this and reuse it. But what if somebody just asks for like 50 ints? Then you got to do 50 and then still have this marked as like free, you know? And then somebody asks for 100 ints, well, it can't fit in here, so it goes up. You know, you got 100, and then somebody like frees this one. Then you've got to recognize the fact that this free area here is next to another free area, and so that's actually a free 150 ints. And so if somebody asks for 150 ints, you'd be like, "Oh, I've got the perfect spot for you, 150 ints right here." And it's like playing a game of jigsaw. And over time, your memory gets really fragmented because you're newing, you're deleting, and so there's areas that are open, areas that are closed, and if every two open areas are next to each other, they merge. So yeah, it's a enormously complicated problem to do. And so as long as all you're doing is news and no deletes, yeah, sure, Sbreak is equal to Malloc when no freeze. Okay, I missed a freeze. Yeah. Malloc does not deallocate memory. There is a function called free that will deallocate memory. And so if all you do are mallocs and no freeze, sure, yeah, Sbreak and Malloc are equivalent. But in reality, you're newing, you're deleting, and somebody's got to keep track of all this, and that's one of the reasons why I say like heap allocations are slow. It's because it's got to go through its data structure and like find a suitable spot. Right? There is overhead. It's not a huge amount. It is an order login algorithm. It's not a huge cost, but it is a cost. And so if you're doing something like billions of times a second, it'll probably be faster to either statically allocate or stack allocate, or you can use what's called a pool allocator, where you just mark off a section of RAM as like, this is what we use for this function every time, and then you're not constantly newing it and deleting it, newing it, deleting it, newing it, deleting it. You just like, this is the RAM that's dedicated to this one function that gets called over and over again, and it just it doesn't have to new and delete every time. So there's a lot of ways around this. For normal purposes, if you're just like making a vector, yeah, new's fine. It's not the overhead isn't that big a deal. But if you have like a vector in a function that gets called a million times a second, then yeah, you might want to start like looking at not heap allocating it and using other allocation methods instead. Smart pointers basically just do the free for you. They don't really impact this at all. The way a smart pointer works is you knew something, and you save the result of the new into a smart pointer, and then when the smart pointer goes out of scope, it frees the memory, so it knows when it's done, and then it automatically releases the memory when it doesn't need it anymore. So they handle the every new needs a delete problem. It doesn't help with this. This is the problem of like memory fragmentation and things like that. It's a really tricky problem. Like, I wouldn't want to write it. You know what I mean? Like, dang, like, how many lines of code is Malloc? I don't even know. So it's like 11,000 lines of code, something like that. Not too many lines on this one, actually. Maybe that's all of it. Let's see. Yeah. Never mind. Never mind. There's a lot more. Okay. Yeah, I'd have to clone it and then see how big their implementation is. All right, you guys work on that. I'm gonna pull the source code. I guess I'll pause the recording now while I investigate the size of the implementation. Okay, you guys got it till noon. Looks like about 6,000 lines of code. Not too bad. Not too bad. So the way that it works is you just put how many bytes you want off the heap. I'm calling it the heap, even though it's just really just moving the data segment pointer up 40 bytes. You call Sbreak, and then it returns a pointer to the chunk of 40 bytes that you just wanted. And then you want to save that into R5. Remember, R0 through R3 are temps. So they get wiped every time you do a branch of link. And then that's your base for the base plus offset calculations. Okay. That's the simplest way I can think of to show you how to do dynamic. That's like a new. Like this is basically malloc 40 or new at 10. All right, so I give you guys an extra 17 minutes of lab time. Logical shift left 1 is to multiply by 2. Logical shift left 2 is to multiply by 4. Yes, every time you do a left shift, it's a multiply by 2, so it's a power of 2. Yes. Lab time is over. So left shift by 3 is multiplied by 8. Left shift by 4 is multiplied by 16. Left shift by 5 is multiplied by 32. So the code that I'm looking at here looks pretty good overall. So here's McCowan's push and pop. You don't need the BXLR. Remember, when you pop, it's writing into the program counter the link register. So these are mutually exclusive ways of returning from a function. BXLR is only used if you're not doing the push and pop method. And you use the push and pop method when you need to save the registers and restore them later. Generally speaking, for small functions, where like, let's say you have a function that's like add x and y together, then you don't do the push and pop, it's wasteful. You just read from R0 and R1, you add them together, save the result into R0, return it, and you have a very fast function that way. And you would use BXLR to return from the function that way. For real functions that are meaty like this, you would use the push and pop, not the BXLR. That was a macro you didn't change. Yeah, it's yeah, just drop the BXLR. It's not needed. So yeah, as far as the speed standpoint goes, we're not too worried about that right now. All right, so this is a little bit redundant here. You could have just made that 128. You know what I mean? Instead, so what you're doing is you're saying like, give me 32 integers. And I get what you're doing. Like you're saying, give me 32 integers. You multiply by 4 because there's 4 bytes per integer. But I would just, make it 128 / give me 32 ints. Something like that. No reason to use an extra instruction to do that. Branch of link to Sbreak. Give me some RAM. Check to see if there's an error. If there was an error, we die. Otherwise, we save the pointer. Okay. And that's your base. And so the problem that Singh had was that he had this inside of the loop. And so every time you called a function like print, that overwrites R0. And so that would mess with your base pointer. Then you're going to segfault. So you might notice how easy it is to segfault in assembly. because if your loops aren't correct, if you have things inside of the loop that shouldn't be inside of the loop, then like resetting your pointer and whatever, then you segfault all over the place. Okay, so that's your base, and then the offset is going to be R1, and so R5 is just the number 4, and R7 is our loop iterator. So it starts off at 0, so the initial offset is 0, then the next time through the run, the loop, it's 1, so 1 times 4 is 4. Okay, so there's your base, there's your offset, that all looks good to me. And you're storing R6 into that element of RAM. R6 starts off at 1, and then you left shift it each time. If you wanted to, you could omit the second parameter there, but it doesn't make any difference as far as the speed thing goes. Either the 2 parameter or the 3 parameter version is fine. Actually, with move, can you omit it? I think you can. I would have to check. So then he adds 1 to I, sees if he's at 32, and again, you don't. Oh, that's why you have that. Okay, all right, I got you. Yeah, okay, that makes sense. And then you jump back up to the top. So a faster way of doing this would be using addition instead. So what I would do is have R1 be the number of bytes, not, you know what I mean? Like, it is the number of bytes as the offset, but rather than redoing the multiply every time, what I would do is add 4 to it every time, because we're going 4 ints to the right every loop iteration. So I would replace this with simply add R1 hashtag 4, and I'd put that at the bottom of the loop. So at the start of the loop, R1 would be 0, and then every iteration of the loop afterwards, I'd add 4 to it, and then you're doing an add every loop instead of a multiply every loop. So it'll be 4 times faster for that instruction. So it would drop your stroke count, your cycle count. Right now it's stores are like 4 basically. So right now you're at 8, 9, 10, 11 inside of the loop, and that'll drop it to 5, 6, 7, 8. So it'd be 30% faster, something like that. And you could probably optimize it further by you could probably get rid of this as well. And you could probably, what I'd actually probably do if I really wanted to make it the fastest, I would start with R1 set to be 128 bytes, and at the top of the loop, I would initialize R1 up here to be 32 times 4, 128. And then at the top of the loop, I would subtract 4 off of it. That's the offset I'm going to write into. Am I going to write backwards? Yes, I am. So I'm going to write the very last element first, and then, so I'd start with, 2 to the 32nd power or whatever, 2 to the 31st power, and store that value, and then I would left shift the value I'm going to write, and I'm going to subtract 4 off the offset, and I would do a subtract and set. And then once the offset gets to 0, then we're done, and we drop out of it. That would allow us to eliminate the add and the comparison. All we would have inside of the loop would be a subtract and set, the store obviously, because you're writing to RAM, the subtract and set, and the write shift. And the, so it'd be six cycles inside of the loop instead of the 11 you have right now. So it'd be about twice as fast. If that's oftentimes how we do it. We go backwards, because when you hit 0, then you can use the subtract and set suffix, and when you hit 0 bytes offset, you're done, and call it a day. Write it in code, sure. All right, be something like this. So the rest of this could be the same. I would move R1 under 28 bytes, start with offset plus 128, and he's already done the Sbreak, and so his pointer is in R4. R4 is his base. I'm not going to rewrite all that code. And then what we're going to do is at the top of the loop, we are going to subtract and set subtract and set R1 4. And then we're going to store into, let's see, and then we would start with the value that he's writing is R6. Move R6. And it would be like, you know, 2 to the 31st power, or whatever that is. I'd put that into R6. And then we would store R6 into base. His base is 4. Offset R1. And then we would do a move R6. Watch, we'll shift right. R6 on the shift right 1. And so remember, we're writing backwards. We're going to start with 2 to the 31st power, 2 to the 30th power, to this, all the way down. And then if we hit 0, branch if less than or equal to done. Otherwise, or it's not even necessary there, I think. Branch if greater than 0 to top. There you go. So that's the loop. So you start at the end and you work your way backwards, and subtract the offset by 4 each time, and then notice I'm very careful that I don't have any comparisons. I don't have any function calls between this. This is where it's doing the comparison, and that's where I'm using the comparison. You have to be very careful about that. If you're going to be printing your integer in here, it'll wipe the comparison, and then you gotta do it all over again, or you know, you just be very careful about where you're setting the CPSR and when you're using the CPSR. That's a very common mistake. Top common mistakes in ARM32. Number 1, confusing B and BL. Number 2, lunging the CPSR, doing a CMP, and then or any command that ends with an S, and then overriding it, like with Sosa's code that we saw earlier. She did a comparison, then she did a function call. If you do a function call, it's going to overwrite the CPSR, the comparison status register. Okay, and then still using it. So just don't use the results of a comparison after a BL, because pretty much every function call you call is going to have an if statement somewhere within it. It's going to wipe the results of your comparison. A comparison's results are saved until you do another comparison. So up here we're doing a comparison. Down here we use it. It's a-okay. But if I had a function call in here, like if I was calling print, then I could not do this, because print is going to overwrite the CPSR. It's a very common mistake. What was the other thing I was going to talk about? Oh yeah, using R0 through R3 with and expecting them to be preserved through a function call. So B is used to jump within if statement or for loop. BL is used for function calls. Yep. If you get those backwards, it's probably going to segfault your code. Yeah, and so same thing. Like, so one of the students had saved the result of their Sbreak in R0, and then you call a function call to print it. Now your base is wiped, because R0 through R3 get wiped out every time you do a BL. Not guaranteed, but there's no guarantee that it will be preserved. So you can't use R0 through R3, do a BL, and then expect them to still have the same values afterwards. You just can't expect that, unless you wrote the function yourself and you know for damn certain, like, R0 through R3 are not touched in that subfunction, but even then I'd feel very nervous about it. It's just safer to use the higher numbers. QC, yeah, this is B, and then if you want to call a function, it's BL print in, right? So BL is a function call. B is to jump to a label within the file. Okay. So this sets the CPSR, and this will overwrite it. And then I'm using it, expecting this value to still be in there, and it's not. So this is a common bug. Yeah. So it just needs an, yeah, then if we were doing that, we would have to do this, then like comparison R1 with 0. Okay. So, or I would move this subtract and set down here and start with it at 124. And then make it branch if... Yeah, I think that works. That way, save an instruction. Yeah, so the way that you structure these things can actually make quite a big difference, right? Whether you have 11 cycles inside of a loop or 6, it just depends on how clever you are in doing your assembly. That's why I've been doing all this code golf with you, so you kind of get into that habit of like counting, like, because that's really where the point of assembly comes in, right? Like, this would be a very easy bit of code to write in C++, so why assembly, you know? For one thing, just so you learn how the CPUs work. That's a big part of it. But also because if you're very clever with it, you can actually oftentimes get performance better than the compiler, especially when the compiler has to play it safe, right? Like if the compiler doesn't know that, you know, when you do a branch with link, you know, like maybe I wrote this function and maybe I know that it only overwrites R0 and not R1 through R3. The compiler would have to preserve R1 and then reload it, and you don't, because like you wrote this function, right? And you know, like you're breaking the contract. Like the contract is R0 through R3 are temporary variables. You can use them however you want. But like if you wrote the guy on the other side, like you know that they only mess with R0 and they don't mess with R1 through R3. Well, you know, you can save yourself quite a lot of cycles that way. And the compiler always plays it safe, and so sometimes you can like be a little bit evil and devious. You have to be very careful with that, though. You have to be very careful because you know, if you rely on, you know, print it not messing with R1, which this is also going to. The way that this code is right now is buggy, right? Because printent is written in C, and C code will step all over R1, and so this code here is no longer valid. Okay, so so like you put in a debug statement, and now your code dies. So you know what I'm saying? Like, because R1, without this code's fine. Without it, the code's fine. It's a-okay. But if you put in a debug statement like, hey, where am I? Now all of a sudden R1, it gets wiped out and your code's seg faulting. You don't know why. You know, it's because anytime you're doing with pointers, you don't want to be your pointers to be getting just set to 0 or whatever. You know what I mean? So, can you push out this file? What file? There's no file. This is just notes. Yeah, I mean, I could put the notes up, I guess. Okay, so let's talk about classes. We got 15 minutes left. And copy lab time to public notes 127.22.txt. There you go. So there's they're the notes for lab time today. So those are the three. Yeah, delete that line, McCone. The reason why I have that is because you can hit undo twice and it'll jump you back to wherever you were before. It's a little hack that I used to use. Okay. Are these examples just printing the number from the register, or accessing the array and printing from there? This example here is writing. It's writing the powers of 2 into the arrays and printing them. It'll print them backwards though. Tilde changes the case on a letter. All right, let's talk about classes. So a class is just an array. Like if you guys are ever curious about how, like what a class is like in C++, how it's implemented in, how it's implemented under the hood, if we have integer A, B, and C, and we see out, let's make a variable to f. If we see out the address of f dot A and the address of f dot B and the address of f dot C, you will see that they're all 4 bytes apart. You understand? So whatever memory address this is, beeb49e4, then the next one's 4 bytes later, then the next one's 4 bytes later. Remember, this is hex. 8 plus 4 is C. 8, 9, 10, 10 is A, 11 is B, 12 is C. Okay. So we've got 3 integers just next to each other in RAM. This is functionally equivalent to like int R3. In fact, if we go R0, you can see that, oh, also, you see how the memory address is different every time. You see that? It's not always the same memory address, right? You don't know where the RAM, you don't know where the base is. It's just figured out by the system. It doesn't matter. The offset, though, we always know. So the offset of the first one, let's say, is 0. The next one is 4 bytes to the right. You see that? 8 becomes C. 8 is 12, right? 4 bytes to the right of 12 is 16. So in the base 16 system, the D becomes an E, and the C becomes an O. And then 4 bytes to the right of that is E4. 4 bytes to the right of that is E8. 4 bytes to the right of that is EC. So you see there's 6 integers, and if I really wanted to do something dumb, let's set f.c equal to 420, and let's see out f.array minus 1. I don't even know if this will work. You're not really supposed to put, yeah, there. You're not really supposed to put negative numbers in square brackets like that. But you see what happened there? So I say, hey, give me the value of an integer 1 to the left, 1 before the array, and that's actually printing the value held in C. Does that hurt your guys' brains a little bit? 0 to 9. Yeah, so hexadecimal is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. F is 15. Then after that, it is 10. 1, 0, 16. It's base 16. 1, 1 is 17. 1, 2 is 18, so on and so forth. So you count up to 1, 9. Then it becomes 1A, 1B, 1C, 1D, 1E, 1F. 1F would be 16 plus 15, 31. When you get to 32, it's then 20, 2, 0. So that's how hex works. So we'll have a lecture on hex. Don't worry about it. But do you guys see what's happening here? Like this struct here is really just 6 integers all next to each other in memory. So a foo is really more or less equivalent to an array of size 6, right? You guys see this? Like all 6 of these numbers, A, B, C, R0, R1, R2, They're all just next to each other in RAM. It's essentially exactly the same as if I had just, like, instead of doing foo f, I could have done, like, integer f square bracket 6. Like, it's going to yell at me because these are the same name, but this is literally, like, basically the same thing from the assembly perspective, right? From C++, it's like, oh, an array of 6 is very different than a foo. These are two incompatible types. But do you guys see what I'm getting at here? Like, for all intents and purposes, these two things are, like, under the hood, they're identical to each other. A class is just an array. But it's an array that can have different types inside of it. Right? It could have a float, you know. It could have a double. Yep. Classes are just arrays. You don't believe me, Fergus? It is. Like, A, B, and C are right next to each other in RAM. R0, 1, and 2 are right next to each other in RAM. In fact, all these three and these three, they're all right next to each other in RAM. And so if I do this, I don't think that's defined behavior under the standard, because I don't know if you can actually pass them. I don't know. I'd have to look that up. I don't think I've ever actually typed this before. And I want to say in my life, but I've probably done it in my life at some point. But, like, I've never done this in, like, professional coding, right? Because why would you? But yeah, that's f dot c, right? Because it's 1 to the left of the array. -2 would do b. Yeah, sure. 2 integers to my left. So f dot b is equal to 100,666. And command not found. Conflicting. Yeah, I told you to be upset at me. Okay. All right. 100,666. Make sense? So the tricky bit gets into, like, if you have, like, a float or whatever in here. Float. Let's not call it f. Float. Right? So the memory address of f dot float should be 4 to the right. Yeah, see that? 8 plus 4 is c. So floats and ints are the same size. So you can just have, you know, a float and then, like, I don't know, another int or something. Four bytes to the right of the array is the float. 4 bytes to the of FLT is D. You see that? It's just, this is an array, but, like, this element right here is a floating point number. From the assembly perspective, it doesn't know anything about that. It's just, you know, it's just an array. But in C++, because we keep track of the types of things, it's, you know, it's different, right? So, what's shifting the hex values? What do you mean when it's a float? These are the memory addresses. This is the address in RAM that these elements are at. So A is here, B is here, C is here, R square bracket 0, R square bracket 1, R square bracket 2. These are not the values in the array. These are the memory addresses in RAM. These are the RAM addresses. Baby. And so after array square bracket 2, we have FLT. That's the memory address of FLT. That's the memory address of D. And you can see all of these people are just 4 bytes to the right of the previous one, because they're all 32-bit numbers. It gets a little bit more complicated when you have mixed 8 bits and 32 bits and 64 bits and things like that. We'll have to have a talk on that, on padding and stuff like that. But When they're all 32-bit numbers, look, like this thing is effectively just 7 ints or whatever, like just 7 times 32 bits, 7 times 4, 28 bytes, from the assembly perspective. Now, C++ knows this value here is a float, so if you were to print out the value in it, so let's set f.float to be equal to 0, and if we were to print fr4, then it prints 0, because as it turns out, 0 and floating point and 0 and integer are the same. But if I set this to like 10, then everything gets screwed up, okay? Because, oh, actually, that was 0 also. Let's see if it's actually finding it. 0. Oh, sorry, that's D. That's float. Sorry. So if you print out -1 as a floating point number, if you break the contract with C++ and you do something like this, this is an integer. Like C++ thinks that array square bracket 3 is an integer. You got an array, your 3 integers to the right, print it out, it's an integer. That's how the C++ type system works. The C++ type system needs to know the type of everything, and I've tricked it, okay? Because there is no fr square bracket 3, right? It goes up to 2. So square bracket 3 is actually the float here. And so I'm actually printing out the float as if it was an integer, and you'll see that it's not going to print -1. It's going to print that, because the bit pattern of a floating point number is complicated enough to have its own lecture. And so it has like no resemblance, except when it's 0. Like if we set it to 0, we get 0. And the reason for that is so that if you just bit fill a chunk of RAM with zeros, you get zeros if they're ints, if they're floats, if they're doubles. Like it's a special thing. Like just all zeros is always 0, But for pretty much any other number, like even if we set it to 1, then you're going to get something that looks nothing like what you thought you were getting. Okay. That's why C++ is shaking. Well, C++ is like, yeah, if you want to shoot yourself in the foot, go for it. It's called a foot gun. like you're being tricky, but you're just shooting yourself in the foot by writing code this way. And C++ has a lot of foot guns. Java and other languages don't allow you to do this kind of stuff. If you did this in Python, it would bounce check for you. You're going out of bounds. No, you're out of bounds. JavaScript does too. Yeah, for sure. Okay, Scout Sheep. I don't know what that means. AOE2. I don't know. So, yeah. So, but do you guys, we haven't written any code with this yet. We'll probably get to that next time. But do you guys kind of see how this would translate into assembly? G++ dash 03 main.cc. Can you do hash tables? Sure, that'd be a fun assignment. Warning, it's out of bounds. Yeah, I know. It's deliberate. Okay, so let's function start. It's being clever. It only saves the registers that it needs, by the way. Okay. So, oh, these are all mangled names. That's the sizeof. Okay. All right. So here is this program, and the our foo is getting allocated off the stack, and then it is going to be putting the value of the memory address into register 0 at some point. R6 goes into there. R0 goes into R6. And it's basically going to be just writing the memory address of like stack. You see this stack pointer 4, stack pointer 8, stack pointer 12, stack pointer 16, stack pointer 20. You see how it's just like an array, right? It's just boop, 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 boop. And so it's just, it's got a pointer, which in this case is the stack pointer, because this is a stack allocated variable. And it's just adding offsets to it and then printing those values over and over again. Plus 24, plus 28, right? So it's, and then when we want to get the value, we do a LDR. You see that? So LDR from the stack pointer, hashtag 24. That's the f dot. This is f dot r star 3. So it knows the offset of r square bracket 3 is 24 bytes to the right of f. So, or from the stack pointer. And then it puts the value there into R1, and then it puts R5, which is probably the pointer to like the print function or something, into R0, and then it calls cout. Okay. All right, so that's it for us today, and hope you guys understand that classes are just arrays that can have different types within it. So they're not quite as easy as an array. With an array, you just add 4 bytes every time. With a class, you have to kind of write down, okay, the array is at plus 16, the float is at plus 24, you know, and then it basically all just works the same way. Okay, so you'll get an assignment on that at some point. For now, just learn. Your homework assignment's going to read the textbook and then do a quiz on the textbook, and it'll be in your textbook readings grade section. Okay, that's it for today. Thanks everyone. See you next time. We'll be back in person on Tuesday. Peace.